In the previous lecture, we discussed about the basic elements, the fundamental building blocks of a communication system. And initially, we talked about the basic building blocks of an analog communication system, and then we also discussed about the building blocks of a digital communication system. Then we also talked about what are the advantages of using a digital communication system as compared to an analog system, right? And we also talked about some of the impairments that happen on a communication channel. So let's quickly summarize that. And in this lecture, we are going to focus on the types of channels and the mathematical models to represent some of the commonly formulated channels which we use for analysis and the design of communication systems. So let us first look at or recall what were the effects or impairments that happen on a communication channel. We call those as the channel effects. Basically, what that means is if a signal propagates through a communication channel, what are the different effects that happen on that to the signal on that channel? And one of the first things that happens is called as attenuation. And attenuation, as we discussed in the previous lecture, is basically the loss of signal strength. Okay, or we can call this as the decay. Okay, the signal becoming weaker and weaker as it propagates further and further through the communication channel. So it's the loss or decay of signal strength with distance. Okay, that's the attenuation phenomena that happens on a communication channel. And then we have additive noise, wherein the noise gets added to the transmitted signal, and the noise on the communication channel can come from internal sources like thermal noise, which is from within the electronic circuitry, and also it can come from external sources. And again, the external sources could be man-made or occurring naturally, which is environmental noise. So in the case of man-made noise, we talked about the ignition from engines, or the signals emanating from other machines, or so on. And in the case of environmental noise, one example that we discussed was the lightning discharges coming from a thunderstorm. Okay, so the additive noise can come from a variety of sources, which could either be man-made or from the environment itself. And irrespective of what the source is, typically additive noise is random in nature. So it's a random noise, and we have to use statistical techniques to analyze and deal with that random noise. The third phenomena that happens is what is called as the amplitude and phase distortion. I don't think I discussed this in the previous lecture, but this is another thing that happens: amplitude and phase distortion. Okay, so the amplitude of the signal could get distorted, or the phase of the signal gets varied. So that causes distortion, and we need to deal with that. And the next aspect that we discussed was multipath propagation. And because of multipath propagation, we get what is called as multipath distortion, which is also called as fading. And fading is characterized by random variations in the amplitude of the signal, because the multiple paths that reach the receiver, they could either add up constructively by being in phase, or they can add up destructively if they are out of phase. So if they are in phase, they will add up constructively and get amplified, and if they are out of phase, they will add up destructively, meaning they will cancel out each other and the signal strength will go down. So multipath distortion results in fading, which is a random variation of the signal amplitude at the receiver side. Okay, so this is called as fading. So these are some of the effects that can happen on a communication channel when a signal propagates through it. And when we design a communication system, we need to make sure that we're able to deal with all these effects so that the signal that is received and recovered is able to compensate for all these effects that have taken place on the communication channel. Now, when we transmit a signal through a communication channel, there are a few constraints also. Whenever we design our system and come up with solutions for dealing with the effects of the channel, there are a few constraints. We can't just adopt any solution of our choice. So there are certain constraints within which we need to develop and design our systems. So let's discuss some of the constraints that we have to deal with. And one of the constraint is the transmit power. So we cannot simply increase the power of the transmitted signal. Okay, if we do so, we can minimize the effects of noise, but there are physical constraints with relation to the equipment and the electronics that are used at the transmitter side. So there is a practical constraint associated with the power level that can be transmitted. So to minimize noise, or to minimize the effects of noise, transmit power can be increased. Okay, but we have practical constraints which limit the maximum power at which we can transmit. So, but there are practical constraints on the transmit power. Okay, and these practical constraints are determined by the equipment used. So the equipment may not be able to produce that amount of power, or it can also be determined due to the interference caused, because if we increase the transmit power, that means our signal is going to interfere more strongly with other users' signals. So it's not simply the case of increasing the transmit power as we like. So we need to take into consideration what happens to the interference caused by our signal to other signals. So that also dictates what should be the maximum transmit power. So we have to take into consideration interference, and of course we also have to take into consideration the health and safety aspect as well. So health and safety. Okay, if we transmit at too strong a power, it can cause a hazard, or it can have in the case of, say, wireless communication, the radiation at higher power can have harmful health effects. So for health and safety reasons, there is a limitation from the regulatory bodies as to how much the practical the transmit power, or the maximum transmit power should be, right? So multiple factors influence what should be the maximum transmit power. So there is a constraint on the transmit power. Second constraint that we face on a communication channel is that of the bandwidth. So the channel bandwidth available for a specific user has a limitation. Let me write that clearly. Okay, so there is limited availability of the channel bandwidth, and as we discussed in the previous lecture, the capacity of a channel is related to the bandwidth available. So if the bandwidth is small, then the capacity of the small channel becomes small, and if the capacity of the channel is small, then the maximum rate at which we can communicate over that channel will also go down. So that the available bandwidth restricts the maximum rate at which we can communicate over a given channel. So the bandwidth constraint arises from the physical limitations of the medium over which we are transmitting. So physical limitations of the transmission medium. Okay, depending on our channel, whether it's a copper wire or a fiber optic cable or the wireless medium, depending on these, we have a limitation on the bandwidth. And a second reason for the limitation of the bandwidth is also due to the electronic components that are used for the transmitter and receiver. So the electronic components at transmitter and receiver. Right? So these also dictate or influence the bandwidth constraint on a communication channel. Okay, so we have talked about some of the characteristics or effects that happen on a channel, and now we have also discussed the main constraints that we have to deal with in designing our system. So these constraints have a direct influence on the capacity of the channel, and just to recall, I want to write down the equation for the capacity of the channel which we discussed in the previous lecture, as the capacity is W logarithm to the base 2 1 plus P by N naught times W. So one of the constraint of bandwidth is showing up in this equation for the capacity of the channel, and the transmitted power P is also showing up in the capacity. So these two parameters, the transmit power as well as the bandwidth, there is a constraint on them. We cannot simply increase them as we wish because there are practical constraints on these parameters, and therefore that limits the capacity of the channel, and therefore that limits the speed or rate at which we can reliably communicate over the communication channel, because the capacity of a communication channel depends on the bandwidth as well as the signal power that is transmitted. Next, we shall discuss about the three major types of channels in terms of the transmission medium. So, types of channels. And this classification is based on transmission medium, and the first type is called as the wireline channel. Okay, wireline channels are used very extensively for our telephone network, so where we have copper cables, copper wires basically, that communicate that link up the devices together. Okay, the communication happens over wired channels. Okay, and the wire is typically made of copper. So wireline channels are of two types. Okay, the first type is called as the twisted pair, and the second type is called as the coaxial cable. So these are the two types of wired communication channels, or wired channels, which are used quite extensively in our telephone network. And basically, these channels are sending the electromagnetic signals by guiding them through the physical medium. And both these channels, both these types of wireline channels have a relatively small bandwidth availability. So, for example, the telephone wire, which uses the telephone wire which uses the twisted pair, okay, gives us a bandwidth of say a few hundred kilohertz, okay, hundreds of kilohertz of bandwidth. So that's a typical telephone wire. That's what we have for the twisted pair. I wanted to write telephone wire here, telephone cable, okay. And the coaxial cable, like for the cable TV network and so on, that offers a bandwidth of several megahertz, okay. So the transmission medium also dictates how much bandwidth becomes available for the channel. So depending on the material and the transmission medium, the available bandwidth becomes restricted. So some channels like the coaxial cable offers higher bandwidth as compared to a twisted pair. But twisted pair is typically used for voice-based telephone communication, and so the bandwidth that is available on a twisted pair is quite sufficient for that particular application. But if you're talking about multimedia content in real time, then communication over a twisted pair will not be sufficient because it doesn't offer sufficient bandwidth for that kind of an application, okay. So the first type of communication channel that we talk about are called as the wireline channels, of which there are two major categories. One is called as a twisted pair and the other is the coax. The second type of channels based on the medium is the fiber optic channel. Okay, and the fiber optic channel is typically carrying the signal in the form of light. So the channel itself is made of glass, very high quality glass material. So the cable that is used for a fiber optic cable, the material that is used for the fiber optic cable is basically very high quality of glass, and it is light signal that is propagated through the glass based cable. So basically it's light being guided internally through the fiber optic cable, and because it is the signal that is propagating through the fiber optic channel is light, so we need to have a source of light at the transmitter side and detector for light at the receiver side. So the transmitter and receiver side are typically an LED or a laser at the transmitter side, and a photo detector or a light detector at the receiver side. So it is guided light that propagates through a glass cable, and for the transmitter side, so TRX is it can be an LED or a laser. Let me write that in capitals. And on the receiver side, typically we have a photo diode or even a photo transistor. Okay, so that's the fiber optic channel, and as compared to the wireline channels like twisted pair and coaxial, fiber optic channels offer a much higher bandwidth. So as I said, the bandwidth available on a fiber optic channel is much larger than what is available on a coaxial cable. And the other good aspect of a fiber optic channel is that the attenuation is very low. That is, the decaying of the signal strength is very low on a fiber optic channel. So that also is an advantage of using fiber optics. So it has low Okay, and therefore, because the bandwidth is more and the attenuation is less, that means, with a much lower signal power, the signal is able to propagate a much larger distance, and therefore, that increases the capacity of the channel, and therefore much higher data rates are possible for when we're using fiber optic channels. And that is why we see that the high speed broadband internet connections are typically using fiber optic channels, even at our homes, right? So that's the second category of channels, which are called as fiber optic channels. And the third category of the channel that we are going to see is called as the wireless channel. Wireless electromagnetic channel. That means the signal is propagating through space as an electromagnetic signal, and typically it's electromagnetic energy being radiated by an antenna, and the receiver side captures or receiver antenna captures that electromagnetic energy, and then demodulates and detects it to get back the original signal or original data. So uses electromagnetic energy So let me write that clearly. So it radiates electromagnetic energy from an antenna. Okay. And again, the frequency at which the signal is transmitted, that depends on the frequency bands available for communication, and also on the available electronic hardware to generate those frequency signals. Now, one of the aspects of the wireless channel is that the size of the antenna from which the signal has to be radiated is dictated by the frequency of the signal itself. And since there is a direct relationship between frequency and wavelength, that means the dimensions of the antenna are related to the wavelength of the signal. So the choice of the frequency that is transmitted on a wireless channel is dictated by the antenna dimensions, because antenna dimension is proportional to the wavelength, and typically the antenna, depending on the shape or the type of antenna itself, the antenna dimension is proportional to, in some cases, 1/4 of the wavelength, or in some cases half the wavelength, or in some cases even 1/10 of the wavelength. So we denote the wavelength typically by the Greek letter lambda. So the antenna dimension is proportional. So we can also write it as antenna. Let me write. Antenna size is proportional to maybe lambda by 4, or lambda by 2, or in some cases lambda by 10 as well. So let's just consider that it is proportional to lambda by 10. That means if you are transmitting a signal of, let's say, 1 megahertz, okay, so for if frequency f is equal to 1 megahertz, then the wavelength corresponding to that particular frequency, since c is equal to frequency times lambda, that means lambda is equal to c by f, right? So that gives us c is the speed of light, which is 3 into 10 power 8 meters per second. So that gives us that lambda is equal to c by f. So c is the speed of light, which is 3 into 10 power 8 meters per second. And with that relationship, we for a frequency of 1 megahertz, that corresponds to the wavelength being 300 meters. Or if we consider that the antenna dimension should be 1/10 of the wavelength, that means the antenna should be at least 30 meters long, and this is a requirement for effective radiation of the electromagnetic energy. So that means the antenna size should be at least lambda by 10, which is 30 meters. Okay, so imagine having a 30-meter antenna on your mobile handset, right? The mobile handset is hardly 6 inches of 5 to 6 inches, and therefore that means a 1 megahertz signal is too difficult to be transmitted or effectively from a small handset, because for effective radiation we are talking about the antenna size being about 30 meters. So that is why typically when we are communicating for mobile wireless, the frequencies used are typically in the gigahertz range. In that case, the antenna size come in the orders of a few centimeters, and that allows effective radiation with smaller antennas, and incorporating the antennas on mobile handheld devices. Okay, it's okay for the mobile tower because that's a fixed station. We can have a 30-meter height antenna, but we cannot have an end user device which has a 30-meter antenna. So therefore the choice of the frequency at which we communicate on a wireless channel is dictated by one of the factors influencing the frequency is the size of the antenna. And because we are having smaller handheld mobile devices, so we need to make sure that the size of the antenna is small enough to be incorporated onto a handheld device, and therefore we have to reduce the wavelength. So reducing the wavelength means increasing the frequency of transmission, so that way the size of the antenna could be kept small and within practical limits. Okay, now on a wireless channel, again, we're going to have the effects of attenuation, multipath propagation resulting in fading, and also additive noise, which is random in nature. So we have to deal with all these effects of the channel, even for the wireless case. Now, in contrast to the wireless electromagnetic channels, where we tend to use higher frequencies because we want to keep the antenna dimension small, there's another type of channel where it becomes more practical to use lower frequency to communicate, and that is what is called as the underwater acoustic channel. And we have a lot of applications nowadays for underwater communications. So in such a case, for such channels where the communication has to take place underwater, lower frequencies are more suitable for communication. Okay, and that's because the attenuation of the signal in the underwater channel increases with frequencies. Yani higher frequencies suffer from higher attenuation as compared to lower frequencies when the signal is propagating underwater. So in underwater case, the attenuation is lower at low frequencies. In fact, the attenuation is lower for low frequencies even in the wireless case, but in the underwater case, the attenuation for higher frequencies is even more severe. So therefore, it makes practical sense that for underwater communication, lower frequencies are used. So attenuation is lower at low frequencies. In fact, the attenuation is prohibitively large at high frequencies. Okay, so that's why for underwater communication we tend to use the lower frequencies, but then transmitting at lower frequencies also requires powerful transmitters, so that the signal, the low frequency signal, can be used for communication. So when we say acoustic channels, it means we are transmitting the signal at acoustic frequencies, and typically acoustic frequencies, we are talking about frequencies below 4 kilohertz. Okay, so for underwater communication, low frequency signals are more suitable because the attenuation is lower for lower frequencies. Another aspect of underwater communication is that if the water is shallow, then it also has multipath propagation, because there could be a reflected path from the surface of the ocean, right, or the surface from the bottom surface of the ocean, and in that case there will be a path propagating to the water, and there could be a reflected path which hits the bottom floor of the ocean or the water body, and then gets reflected from the bottom and comes back to the receiver, right? So in that case, there will be multiple components arriving at the receiver, and when there is multipath propagation, the immediate effect that we see is the effect of fading, where the signal can vary randomly in amplitude because of constructive or destructive interference taking place between the multipath components. And as in the other channels, there could be external random noise, and in the case of ocean, the external noise could come from the sounds made by the aquatic animals, and also from ships or other forms of equipment that may be in the ocean. Typically, if the communication is taking place closer to the harbor or port, there is going to be a lot of noise coming from man-made sources like ships or the other equipment available at the ports. Okay, and the fifth type of channel is what is called as the storage channel. Okay, and storage channels, we may not actually immediately think of it, but the storage channels is where you have data stored on say a hard disk or a magnetic tape or a CD, and the data has to be moved from that the storage device to a screen for viewing, or to a speaker for listening to the music if it's an audio signal, or if it's a video signal, the video has to be transferred from the storage device through the cables internal to the computer and onto the computer screen so we can see it. Or if it's a text file, again the data is stored as bits which we need to move from the hard disk, which is connected through the cables, and eventually it comes to the screen for us to read it on the screen, right? So there's a lot of transfer of information taking place from the storage devices to the output transducers, which could be a speaker or a screen or any other form that is, and we need to move the data from different parts of the computer itself, or maybe from the hard disk to the RAM and onto the screen, or when we type some key on the keyboard, that information has to propagate internally and then save it in the file, for example, if you're typing something. So there's a lot of movement of data happening within our devices, from our storage systems to our screens and so on, and the path between the storage device and the screen, or the path between the storage device and the headphone or speaker, those constitute what is called as storage channels. And typically there is some form of channel coding used to protect the data, so for such kind of channels, so there is some channel coding, For example, on your CD, if there is a scratch on the CD, the data which is stored in that particular part of the CD could be corrupted, and we need to retrieve the data somehow. So there is some channel coding employed to detect whatever errors that might have happened in that data and try to recover them. So storage channels use channel coding to recover corrupted data. And even these kind of channels can have external additive noise, because when the data is moving from your hard disk to your screen through the internal cables, there could be external noise from other electronic devices within the computer. So all these can affect the signal in a bad way, and we need to deal with these things. So that's another type of channel that we want to just be familiar with. But the main focus of this course is going to be on wired and wireless channels, which have additive noise and multipath propagation causing fading, and we'll discuss the different techniques of dealing with those effects. So, having seen these 5 types of channels based on the medium and and the environment in which they are used, we will now move on to mathematically model the most common types of channels that we encounter. So, the next discussion that we're going to do is called as the mathematical models for communication channels. Now, why do we need a mathematical model? It's because we need to characterize the channel and represent it in a mathematical way, because there are many effects happening on the channel, like attenuation and the addition of noise, multipath propagation, and so on. So if we can represent all these effects into the mathematical model of the channel and get a mathematical model of the channel, then we can use this model to design our transmitter and receiver side to deal with those effects. So having a mathematical model makes it convenient to design the channel encoder or modulator at the transmitter side, and the decoder and demodulator at the receiver side, for example. Okay, so we therefore need to have, and for the sake of convenience and analysis, it becomes useful to have mathematical models for a communication channel. And the first type of mathematical model is what is called as the additive noise channel, where the noise gets added to the transmitted signal, and that is the most basic type of channel, additive noise channel. So the effect on this channel is that whatever signal we transmit, the channel adds some noise to it, and the received signal is basically the sum of the transmitted signal and the noise component that gets added by the channel. So we can basically describe this in terms of a block diagram as So the additive noise channel can be modeled as in this diagram here, where we have the transmitted signal S of t and the noise signal N of t, and the channel gets the noise added to the transmitted signal, such that the received signal is basically the sum of the transmitted signal and the noise signal. So the received signal, if we call it as R of t, is basically equal to the transmitted signal S of t plus the noise signal N of t. Okay, so that's the block diagram representation of the additive noise channel. And the mathematical model for this channel is simply going to be R of t equal to S of t plus N of t. And that's the most basic simple type of channel. And it's the additive noise component is always one of the omnipresent aspect in almost all types of channels. And in such a channel, the noise N of t is typically it's a random signal, so it's random, and it has a Gaussian distribution, so it's random. Or typically we find that it is with the Gaussian distribution. Okay, and because it's the additive noise is having a Gaussian random distribution, such a channel is also called as an AWGN channel, AWGN, and that stands for additive wide Gaussian noise channel. Additive white Gaussian noise channel. Okay, the white term comes from the fact that the power spectral density of Gaussian noise is flat. So it's flat means it has all frequency components in equal proportion. So therefore we also call it as white. And typically the additive noise channel is referred to as the additive white Gaussian noise channel because of the fact that the random distribution for the noise samples follows a Gaussian distribution, and the power spectral density is also flat, so we call it as an AWGN channel. Now in this mathematical model, if you want to incorporate the effect of attenuation, so we can simply, attenuation is basically the signal strength decaying with distance. So we have to just incorporate an attenuation factor into this equation to include the effect of attenuation. So with attenuation, we can write this model as R of t equals A times S of t plus the noise points. Okay, so it's additive noise, and we have included the attenuation factor A here. So A is the attenuation factor of the channel. Okay, so now we have a mathematical model for an additive noise channel including the attenuation factor, which has been denoted as A. The second type of channel mathematical model that we are going to have for a channel is with additive noise and with additive noise, as we have in this case, but we also incorporate a filtering model into it because in many communication applications we use linear filters to prevent the signal from exceeding a certain bandwidth, so that the signal stays within a certain bandwidth to avoid interference to other users. So if there is some filtering effect happening at the transmitter side and at the receiver side also, then we need to model this channel as by including the effects of that filtering. Of course, with that we'll have the additive noise as well. So the second type, second mathematical model that we are going to see is called as the linear filter channel. And of course that will also include the effect of additive noise. So typically this linear filter channel arises when we use filters to band limit a signal. Okay, arises when filters are used to limit the bandwidth of a signal. So in this case, we need to represent those filters using their impulse response. So the channel model would be like using the impulse response of the filter, so which we call as h of t, and let's put that in a box. So that's our filter. So that's the impulse response of the linear filter that is used to limit the bandwidth of the signal. And to this there is an input signal which we call as s of t. So the input signal, as usual, we call it as s of t, and the output of the filter gets added with the noise. So the additive noise component is also there. So the noise part gets added here. So if we can make an arrow here for the noise component, so that's n of t, and then we get here at the output the result of the channel, which is basically the received signal, which we denote as r of t equals. So this is the impulse response of the filter, of the linear filter. So the output of the linear filter is going to be the convolution of the input and its impulse response. So what we're going to have here is s of t convolved with h of t. So the output of the linear filter is s of t convolved with, I'm writing the convolution operation by the star inside a circle. So I'll just write it as a star, s of t star convolved with h of t, and to that the noise gets added. So the received signal is the convolution of the input signal with the impulse response plus the noise signal n of t. So that's the next model we have, which is called as the linear filter with additive noise. So this is the linear filter channel with additive noise. Okay, so the entire channel model is shown within the dotted line here. So that's our channel. Okay, which has a linear filter component given by its impulse response h of t, and the additive noise component here given by this plus sign, and the noise simply gets added to the convolution of the input signal with the impulse response of the linear filter. So that's our second model that we have for the in terms of the mathematical model of the channel. And the third model that we are going to discuss is similar to this linear filter channel, but it's a time varying impulse response. So suppose that the linear filter has a time varying response, then it gives us a time varying channel, and that is typically what we see in the wireless case, where the channel is not fixed all the time. Okay, the characteristics of the channel change with time, they vary with time. So we model such a channel as a linear time variant filter channel. So here we have the impulse response of the filter, which is linear time invariant. That means the impulse response does not change with time. The impulse response remains the same, at all of the linear filter remains the same. But in a linear time variant filter channel, the impulse response is going to change with time, and correspondingly that would indicate that the channel is having characteristics which are changing with time. So in this case, what is going to happen is the linear filter is going to be having an impulse response that is varying with time. So we'll now denote the impulse response as h of some tau, but that is varying with time. So depending on at what time we are checking the impulse response, we get a different response. So we include that t as well. So that's the time varying impulse response. So h of tau colon t is the impulse response at time t. Okay, it's the impulse response of the linear filter, that is. Okay, and the input signal is we'll denote it as s of t. So we have s of t denoting the input signal, which is input to the linear time varying filter, and the output of the filter gets added with the noise on the channel. So the noise component gets added here. So we'll have n of t over here. So we'll denote that as n of t, and the output of the channel is basically the convolution of the input with the channel impulse response or the linear filter impulse response plus the noise component. I'm just going to make that arrow a bit smaller. So the received signal R of t in this case is the convolution between the transmitted signal S of t and the time varying impulse response, which is denoted as h of tau colon t plus the noise term n of t. So that's a linear time variant filter channel with additive noise. So this entire block, we can put this whole block together to denote the channel. Okay, and I'm just going to make it as dotted line. So that whole thing denotes our channel, which is shown in dotted line. Okay, so that's a linear time variant filter channel. Basically, the characteristics of the channel are changing with time. So typically, channels where we have multipath propagation are modeled as this kind of channel. So channels with multipath propagation okay, because the multipath characteristics are not going to be the same all the time. How the reflection of the signal is going to take place on different objects and reaching the receiver, they know that's going to keep changing with time. And when that happens, the multipath propagation characteristics are changing with time, and therefore the channel characteristics are changing with time. And that is typically what we see in wireless communication as well as in the underwater acoustic channels. So channels with multipath propagation are typically modeled as linear time variant filter channels. Linear time variant, that means they are varying with time. The characteristics of the channel are varying with time. So it is modeled as a linear time variant filter channel with additive noise. Okay, so that is the third category of the mathematical model for the channel. All right, so that brings us to the end of this lecture, and just to summarize, what we have seen today in this lecture is the types of channels and the mathematical models of the channel. So we have seen several types of channel. Let's quickly recall them. So we have seen, we did the review of the channel effects from the previous lecture, and then we also discussed about the two constraints that we encounter. One is that of the transmit power constraint and the bandwidth constraint, both of which influence the capacity of the channel, which in turn affects the rate at which we can communicate on a physical channel reliably. And then we talked about the types of channels, which are broadly classified as wireline channels, fiber optic channels, wireless channels, underwater channels, and finally the storage channels. And then we have discussed about the three common types of mathematical models for the communication channel. The simplest type is the additive noise channel, where we are dealing only with additive noise, and we can incorporate the attenuation factor in that in the mathematical model by incorporating the attenuation factor into the equation. Okay, so that is basically this model represents a channel which has the effect of attenuation and additive noise. Next, we discussed about the linear filter channel, where the effect of filtering is also incorporated into the mathematical model of the channel. So that way, the linear filter used at the transmitter side for limiting the bandwidth of a signal is also considered as a channel effect. So that way, the linear filtering is given as the convolution of the transmitted signal with the impulse response of the linear filter, to which the noise gets added. So we have the linear filter model for the channel with additive noise. And then for time varying channels, we have the linear time variant impulse response of the filter. So in that case, we have the output, the received signal R of t, as the convolution between the transmitted signal and the time varying impulse response of the linear filter, to which the noise gets added. So that's a linear time varying filter channel with additive noise. And typically this is the model that we see for wireless multipath propagation channels and also for underwater channels. Okay, I'll stop here for today, and we will continue with the next topic in the next lecture.